So I'll just start. Hello, everyone. I'm very happy to welcome our today's speaker, Professor Soydan from Turkey. And before starting with the talk, I would like to request you all to keep your audio on mute. There will be a question answer session at the end. Nevertheless, if you have any question, you can do it over the chat box. And please wait for a signal from our coordinator, Professor Shanta Leshram, before unmuting your audio. Welcome, Professor Soydan. We can start.
Yeah, Gökhan, please. You can now please start.
Okay.
I think he's frozen. So can you hear me?
Hello, Professor Soydan.
Okay. I think he has.
He's lost the connection.
Okay, now he's back. Yeah. So yes, Gökhan, now please unmute. Then you can please start the seminar. Yeah, can you please share the screen? Hello, Gökhan, can you hear me?
Can you hear us?
Actually, you're muted. Can you unmute your? Can you please unmute your yourself, because you are muted. There's no voice from your side. You're not audible. We can't hear you. I think you're still muted.
Can you hear me?
Yeah, now we can hear you. Yes.
Can you see my screen?
Not yet.
Now?
No.
No.
Please share. No. Please share once again. Please click on the share now. Still now we can see. Okay.
Yes.
Now we can.
Can you make it full screen now?
Yeah. Now.
Okay?
No.
Yeah. Now it's fine.
Now
Yeah.
it's fine.
Please.
Okay. Can I start?
Yeah. Yes. Please.
Okay. Good afternoon, everybody. First of all, I would like to thank to Professor Shanta Laisram for kind invitation to webinar. I will talk about some recent results on two Diophantine equations with power sums. My talk consists of these titles. First, I will introduce Bernoulli numbers and Bernoulli polynomials for young researchers. Then I will give some important examples about the applications of Bernoulli numbers. In the second title of my talk, I will show the connection between power sums and Bernoulli numbers and Bernoulli polynomials. Then I will introduce Schaffer's conjecture, which is about a Diophantine equation with power sums. And I will try to power sums, and I will try to summarize all advances about Schaffer's conjecture. In the third title, I will give my old and new results about a Diophantine equation with power sums. In the final section, I will first introduce a Diophantine equation of power values of the sum of three squares in arithmetic progression. Then I will give some examples from literature about these type equations. Finally, I will introduce my recent results with Maohua about this equation. Okay. Jakob Bernoulli, moment please. Jakob Bernoulli introduced, who is Swiss mathematician, introduced the Bernoulli numbers in connection to the study of the sums of powers consecutive integers. In his book, its name is Ars Conjectandi. It was published in 1713. We know these formulas from almost secondary schools. But Bernoulli expressed the right-hand side without factoring. He gives a general formula involving the numbers which are known today as Bernoulli numbers. Bernoulli explains how these numbers are determined inductively, and he emphasizes how his formula is useful for computation, the sum of powers. This is interesting. He claims that he did not take a half of a quarter of 1 hour to compute the sum of 10 powers of 1 to 1000, which he computed correctly as this number. This is a big number because it was 7th century. Using modern notation, his formula is written in this form. Here, Bj is called a Bernoulli number. Tj is the binomial coefficient. You see this relation. We can compute all consecutive powers with this formula using Bernoulli numbers. At the same time, Japanese mathematician Seki Takakazu published a paper, and 1 year before Bernoulli, his formula and definition are completely the same as Bernoulli's. This is interesting. Since the discovery of Bernoulli numbers, we see that there are many applications, including the series expansions of trigonometric and hyperbolic trigonometric functions, the Euler-Maclaurin summation formula, the evaluation of the Riemann zeta function, and Fermat's last theorem. A very extensive bibliography on Bernoulli numbers. You can look Carl Leischer's website, who is Canadian mathematician. This is website. There are many useful informations about Bernoulli numbers. Okay, a sequence of Bernoulli numbers is given with this recurrence relation. This is initial values. B0 is 1. Then we can find another Bernoulli numbers. As you see, the first Bernoulli numbers, BQR, given in this table. And note that the odd Bernoulli numbers with odd indices are 0, as you see, B3, B5, B7, and all Bernoulli numbers with odd indices are 0. Okay, we can use generating function for Bernoulli numbers. You see here Bn is Bernoulli number. The connection between Bernoulli polynomials and Bernoulli numbers is given with this relation. The first few Bernoulli polynomials BQ are given as follows. Bernoulli polynomials. Okay, I will try to some examples about applications of Bernoulli numbers on number theory. This is the first example. One of the most powerful applications of Bernoulli numbers, the evaluation of Riemann zeta function. I'm trying to give some notions clearly for young researchers. Let key be a real number. Absolute value of key is at least 1, then the Riemann zeta function over real numbers, zeta key, is defined with this formula. This function is important for many reasons, but we will highlight one result proven by Euler related to the prime numbers. For keys greater than 1, zeta key is given also with this formula, or over all primes P. Okay, Bernoulli numbers help us to calculate even values of this function. As you see, zeta 2 key Riemann zeta function for zeta 2 key values, we see that Bernoulli numbers with even indices. And Riemann zeta function is more famous as a complex function with powers key in the complex plane. In 1859, Bernard Riemann hypothesized a result related to complex Riemann zeta function, namely that all of its non-trivial zeros lie on the line x is 1, 2 over line. Riemann hypothesis has never been proven and remains one of the greatest unsolved problems of mathematics. Okay. Mathematicians and mathematical physics have developed whole branch of mathematics contingent on the fact the hypothesis is true, so that anyone who manages to uncover the proof will immediately verify thousands of results. Okay, the second example about Fermat's last theorem. Now, we look at the application of Bernoulli numbers to one of the great solved problems of mathematics. Fermat's last theorem says that this equation has no integer solutions x, y, z for positive integers and is greater than 2. Ernst Kummer, who is a German mathematician, had spent little time on Fermat's last theorem. He considered the accuracy of number theory rather than a major item until March 1947, when the French mathematician Gabriel Lame published a complete proof of the theorem. Lame's main contribution was noticing the sum x to the n power x to the power n plus y to the power n could be decomposed into factors involving the n roots of unity, you see. It was a useful step. However, he incorrectly assumed that this factorization was unique in Q zeta p, but Kummer had proven years prior that this was not the case. Kummer felt compelled to respond, and the few weeks later, Lemme's publication, he had a proof for a select group of integers, and that would satisfy Fermat's last theorem. Then Kummer called them regular primes. Odd prime p is regular prime if the class number of q zeta p is relatively prime to p. Note that by definition a class number is the order of this class group zeta p, but more intuitively the class number can be understood as scalar quantity describing how close elements of a ring of integers are having unique factorization. If the class number is 1, then the ring has unique factorization. For positive values greater than 1, the closer to 1 the class number is, the closer to having prime factorization. Kummer proved an equivalent equation which almost magic involves the Bernoulli numbers. He defined this: a regular prime p is an integer such that it does not divide the numerator of these Bernoulli numbers. Kummer proved Fermat's last theorem for all regular primes. This, of course, begs the question, how many regular primes are there? We know that the first regular prime is 37, because you see this relation. Beyond that, we know that there are infinitely many regular primes, but it is not known if there are infinitely many regular primes. Computational studies have shown that about 60 primes of regular. German mathematician Carl Ludwig Siegel has conjectured that the exact proportion converges to e to the power -1 to over. However, neither hypothesis has been confirmed. Regardless, Kummer's early work into Fermat's last theorem paved the way for mathematicians the 20th century to finish off the problem. Okay, now I would like to give first result. In 1875, the classical question of Lucas was whether this equation has only the solutions this. In 1918, Watson proved that this equation has no solution other than this. Now we consider this Diophantine equation, consecutive power sums is equal to y to the n. This is the most important relation. This relation shows that Bernoulli polynomials and Bernoulli numbers has very good connection with consecutive power sums. You see, this is Bernoulli polynomial, Bernoulli number. Okay. In 1956, Schaeffer gave this theorem: if K is 1, this formula is sorry. Okay, Schaeffer defined a polynomial for the right-hand side of this polynomial skx if k is greater than 1 odd skx equals this expression. If k is greater than 2 even, skx is equals to this expression. ck is positive, ck is integer coefficients, Rkx is a polynomial with integer coefficients. And then Schaeffer proved the following result. For fixed key is at least 1 and is at least 2, the equation 6, this equation has at most finitely many solutions in positive integers x and y, unless these solutions, in each case, there are finitely many solutions. Schaeffer proved this theorem, this result. Schaeffer proved that this equation has finitely many solutions in each following cases. In the terminology of his works, XY11 was called as trivial solution, X and Y 2470 was called as non-trivial solution with key n22. Schaeffer gave the following conjecture: let key is at least 1 be fixed and let n is at least 2 be positive integer with key n not in the above list. Then the equation 6, this equation, has only non-trivial solution key and xy 2470. Schaeffer gave this conjecture in 1956. In the last 50 years, you will see many results about this conjecture. First progress was recorded in 2003 with the following result. Jacobson, Pinter, Walsh proved that Schaeffer's equation has only non-trivial solution except in the case key is 2 when there is an enormous solution x and y 24 and 70. They proved that this equation for n is 2. They solved the case n is 2, key is smaller than 58. And then next year, Bennett, Gurry, and Pinter gave this theorem. They solved this equation for key is between 1 and 11, key and not in the set of 10. These values. Yes, they proved this result. 11 years later, any progress on Schaeffer's conjecture was recorded by Hajdu. We call that Bpn stands for the exponent of the prime p in the factorization of positive integer n. Hajdu gave this lemma for proving his results. Let's x be positive integer, then we have v2 skx function, and he used periodic valuation functions V2, and then he used V3 periodic valuation function. Using these periodic valuation functions, Hajdu proved that Scheffer's equation has only non-solutions, but x is when x is congruent to 0 or 3 in modulo 4, x is smaller than 25. Under these conditions, Hajdu proved this conjecture. And the next year, Hungarian mathematicians Berzés, Hajdu, Pint, and Japanese mathematician Takafumi Miyazaki considered Scheffer's conjecture. Again, they proved that all solutions of Scheffer's equation in positive integers with x is smaller than 25 and n is greater than 3, they found these solutions. And as a simple consequence, they obtain the following corollary. For x is smaller than 25 and n is at least 3, Scheffer's conjecture is true. As you see, there is no progress about Scheffer's equation since 2016. Scheffer's conjecture is still open. These authors did good progresses, but the conjecture has not been proved completely yet. Okay. Now we consider this equation, TQLX polynomial is equal to y to the n. In 2013, Zhang and Bai worked this equation for the case K is equal to L is equal to 2. They gave this following result. They solved this equation for this case, which means L is 2. And then 4 years ago, I considered this equation. I proved that this equation has finitely many solutions where L is even. I proved that in 2017 for the case L is even. I couldn't prove for the case L is odd. By this theorem, it was proved that this equation has finitely solutions. The case n is 2 and k is 1 or 3, this equation reduced to Pell's equation, which means it has infinitely many solutions. K is 1 or 3, y is equal to 2, n is equal to 2. Okay.
Rokan, I have a question here. So, can you please go to the previous slide? No. Yeah, this one.
Yes.
Here, so if you see the difference between theorem 11 and 12, so in 11 you have you're fixing k. Okay, k and l are fixed, right?
Yes, I bounded n, only n. The second theorem, I bounded x, y, n like this.
Okay, okay. So I see. So in the first one, you okay, you bound only n. Okay, please continue.
Okay. We need some lemmas proving theorems 11 and 13. As you remember, this equality is related to Bernoulli polynomials and Bernoulli numbers. And another important result It was given by Bella Brinza in 1984. This is most important result. I will cite to this paper in the next slides. Hx is a polynomial which has degree n, and these are roots. Ri is okay. B is different from 0. M is at least 2, and define Ti. Suppose that T1, T2, and Tn is not permutation of the n tuples. I recall them bad patterns, because except for these bad patterns, this equation has finitely solution. If we don't catch these bad patterns, we see that our equation has finitely many solutions. This is very useful result. I will use it. Okay. Another useful result in 1976, Andre Schinzel and Rob Tijdeman gave this result. Fx is a polynomial with rational coefficients having at least 2 distinct roots. Then there exists an effective constant such that any solution of this equation x n belongs to z, y belongs to q satisfies this relation. Another useful result, if we can prove that the polynomial fx has at least 3 simple roots, we prove that this equation has at most finitely many solutions when the case n is greater than 1. Or if we can prove that the polynomial fx has 2 simple roots, then this equation has finitely many solutions with n is greater than 2. 3 simple roots. This case, 2 simple roots is this case. Okay. And we need 2 key lemmas. This lemma shows that connection between Bernoulli polynomials and my equation. Okay. We proved that this polynomial has at least 2 distinct zeros. Okay. And the second important lemma, BQX is the cute Bernoulli polynomial. This polynomial, but in this case, we suppose that L is even. This polynomial has at least 3 zeros of odd multiplicity, unless Q is equal to Q belongs to this set, because in this case our equation reduced to Pell's equation. We are interested in finitely solutions. For any odd prime P, at least 2 zeros of Px have multiplicities relative prime to P. Okay. The idea for the proof of theorem 11, we are trying to solve this equation. This polynomial has at least 2 distinct zeros. We proved it, and hence using Schinzel-Tijdeman's lemma, we can prove that this equation has finitely many solutions for the case n is greater than 2. And another theorem, we know from theorem 11. Okay. N is bound. So we may assume that Nx fixed using Brinzas lemma and Soydan lemma. We can prove the rest of the part of the theorem. Okay, this is old result. It was published in Publicación Mathematica de Bresen Journal 2017. There was a gap in this paper for the case L is odd. In the last year, I and my colleague Daniele Bartoli solved the case L is odd, so we completed the gap for this equation. Okay, we remember this relation, and then TKLX, we see that 0 is root of this polynomial TKLX polynomial. If k plus 1 is odd, the multiplicity of 0 is 1. If k plus 1 is even, the multiplicity of 0 is 2. Okay. This is the first result about the polynomial TKLX has at least 3 distinct roots. The proof is easy, but I couldn't see it for 4 years ago. We proved in this theorem. This is elementary proved. TKLX over this expression is equal to this expression using the expansion of this polynomial and binomial coefficients. We get a contradiction because we suppose that TKLX has only 2 distinct roots. I skipped the elementary details. We get a contradiction. So the proof is completed. The second important result, we proved that this equation has finitely many solutions for the case L is odd. So we gave the general result for this equation. This equation has finitely many solutions. Okay. For the proof of this theorem, we have 2 cases. We suppose that k plus 1 is odd and the multiplicity of the root of 0 is r is 1. In this case, T0, you remember, I think we should go back to Brinzas result. We need it. Yes. This is polynomial, and Brinza defined this relation Ti. This is M, Ri, the multiplicity of the roots. Ri is the multiplicity of the root Ti. Our proof depends on Ti. If we don't see bad patterns, we will prove that our equation has finitely many solutions. Okay. Okay, T0 is equals to N. We know this relation about Bernoulli numbers using the term of degree of 1 of TKLX. We have this equality, Bi is the ith Bernoulli number. And then we have 2 subcases. N does not divide K. In this case, we have n is 2, which is impossible. Therefore, n is greater than 2. In this case, we have this, and therefore, bad patterns in lemma, Brinzas lemma, are avoided. This is not bad pattern. So we are successful in this case. In another case, we used an important result of von Staudt-Clausen theorem. According to this theorem, Bernoulli number B key is different from 0. 2 divides the denominator, but 4 does not divide of this Bernoulli number. In this case, if 2 to the a is the highest power that divides L minus 1, then this is the highest power which also divides this expression. Therefore, 2 divides, and 4 does not divide the denominator of alpha 0 to the n, which is a contradiction. In this case, if there exists at least one root having multiplicity Ri divisible by n, then pattern does not correspond to. So this is a good news. So this case is completed. Okay. I'm skipping another details. The main idea is Bella Brinzas papers to use patterns. I'm skipping. You can use these results in my papers. You can access it in archive, or it was published in Publicazione Matematica del Recent 2020, and I skip these details. Now, I would like to mention another equation. This is very new. This equation is about the power values of the sum of 3 squares in arithmetic progression. Now, I would like to give some earlier results about this equation. This equation was solved completely by Zhongfen Zhang for the case 2, 3, 4 in 2014. Actually, Cassels considered this equation in 1985, but he considered this equation for the case key is 3, n is 2. Okay. And 2 years later, Bennett, Patel, Sikseck extended Zhang's result. They solved this equation for the case keys 5 and keys 6. The same year, Bennett, Patel, and Sikseck considered this equation. They used modular methods and linear forms in logarithms. They solved the case key is 3. Sorry. I skipped this equation. This equation should be x to the power key plus x to the power x plus 1 to the power key x plus, moment please.
Yeah. So Gokhan, any issues?
Can you see this screen?
Yeah, we can see the screen.
Okay. Bennett, Patel, and Zygzak consider this equation. R is yes, they solved this equation. I go back my slides. Okay. In 2017, 2019, Zhang, Kotsianas, and Patel studied the integer solutions of this equation. This is more general. According to this equation, you see D instead of 1. Zhang solved this equation for the case key is 4. Kotsianas and Patel studied the integer solution of this equation. Key is 2. Okay. Zhang used a modular approach. Kotsianas and Patel gave all non-trivial primitive solutions of this equation when the case key is 2, n is prime, d is smaller than 10 to the 4. Okay, and Garcia and Patel showed that this equation showed that the only solutions to this equation n is at least 5 prime, key is 3, x and d are co-prime, d is between 0 and 10 to the 6. The trivial one satisfying xy is 0. Okay. Recently, Kotsianas studied the equation, this equation for the k, for the case key is 2. Key is 2. He showed that n is odd prime that satisfies this prime power. P is at least 10 to the 4. Then all solutions of these equations are given the following table. He considered this equation for this case. Okay. In the new result, with I and Maohua considered this equation for the case this prime power and P is general. P is general, not bounded. Kotsianas considered this equation, P is smaller than 10 to the 4. In the new work, we considered this equation, P is general. Of course, we have some conditions. We prove following results. This is the first result, n be odd prime, let d be prime power, like this. If xy is the solution of this equation, p is greater than 3, and d is given this relation. Moreover, if this relation holds, then the solution xy can be expressed as this relation. X and y are like this for this equation. Another theorem, under the assumption of previous theorem, this equation has at most one solution, x and y. Another result, let n be odd prime if every odd prime divisor p of these satisfies. P is not congruent to plus minus 1 in modulo 2n, then this equation has only the solution xy dn, the solution. And the final solution, if n is greater than this number and d is greater than this number, then all solutions xy of this equation satisfy this inequality. We have main results. I will try to main ideas and
yeah, Gokhan, so is that for any D?
sorry?
Is this result like theorems?
Yes, yes. For any D.
For any,
yes, D is prime power.
okay,
P to the R. P is greater than 3. Yes, this is more general than Kotsianas results. Okay?
No.
What is the problem?
No, please continue. That's fine. Please continue.
Okay. Okay, I would like to recall some definitions for young researchers. For fixed integers ABC, the homogeneous quadratic polynomial. This quadratic polynomial is called a binary quadratic form, or simply a form is denoted by this notation. The integer d is called the discriminant of the form, of this form. Okay, we need quadratic primitive forms. Let d1, d2 key be fixed positive integers such that minimum of d1, d2 is greater than 1. Key is odd, and d1 and d2 are co-prime, and d1 times d2 and key are co-prime. Let h minus 4 d1, d2 denote the class number of positive binary quadratic primitive forms with discriminant minus 4 d1, d2. Okay, we need, firstly, we need this lemma. This equation has solutions, then its every solution x, y, z can be expressed as these relations where x1, y1, z1 are positive integers such that this relation. The proof of this lemma is used a paper of Maohua. It was published in 1999 in Journal of Number Theory. This is a special case of his theorems. Okay, we need another lemma. If our equation, when at an odd prime and d is prime power, p is greater than 3, this equation has solutions xy, then n is odd, and its every solution xy can be expressed as these equalities. If we can expand this polynomial and if we factor this polynomial, you will see the one-off factor is this. We use this factor, x and y is here. Using Maohula's lemma, the proof of lemma, this lemma can be done. Now, I would like to recall Lemma sequences and primitive divisor theorem. Alpha, beta, b algebraic numbers. Alpha, beta satisfies, alpha and beta are satisfied this relation. In this case, alpha, beta is called a lemma pair. A and capital A is equal to alpha plus b squared. C is alpha times beta. Alpha, beta is like this. Such AB is called the parameters of lemma pair alpha, beta. And then two lemma pairs are called equivalent if alpha 1 over alpha 2 is like this. If these are equivalent lemma pairs with parameters capital A1, capital B1, and they are respectively, then capital A2, capital B2 is equal to this expression. Lemma number is defined by this relation. Okay, and this is important theorem, primitive divisor theorem. Alpha beta be a Lemma pair. A prime number Q is called a primitive divisor of Lemma number if Q divides Lm but does not divide this expression. We say that a Lucas sequence is an M-defective Lemma sequence if Lm has no primitive divisor. Okay. In 1995, Paul Vautier gave a useful table. This table gives n defective Lemma pairs are given in this table. And another important result, it was given by Biluhanrod Vautier in 2001. Every positive integer m with m is greater than 30 is totally non-defective. I will try to sketch for the proof of main results using lemma 13. We have this lemma 13. Remember, this is lemma 13. And D is prime power. By using this equality, we have this expression. Let alpha and beta like this, and then we are checking necessary conditions to be Lemma pair with these parameters. And then in this step, the definition of Lemma number, we have this is a connection between our equation and Lemma number. Therefore, we have this equality. And then using Vautier theorem and Biluhanrod Vautier theorem, we see that if Sn is greater than 0 by primitive divisor theorem, then Lemma numbers has no primitive divisors. And using important theorems, we see that we obtain only the case n is 3 or 5. In this case, using elementary arguments via congruence and Legendre symbols, we get contradictions. So we can complete the proof of theorem 13. Another proof of theorem is easy under the assumption of theorem 13. This is theorem 13. Using this, we can prove this theorem. This theorem says that this equation has at most one solution, x and y. Okay. For proving another theorem, we need Lemma lemmas. Lemma lemmas says that if n is odd prime, Q is an primitive divisor of Lemma number, then Q is congruent to plus minus 1 in modulo 2n. Using lemma 19, we get this relation, and then we have this using same procedure, using Vautier theorem, the theorem of Biluhanrod Vautier. We can deduce this expression, and we have n belongs to this set. In both cases, using elementary arguments, we get contradictions, so the proof of theorem is completed. This is the last theorem. Now we need some Baker's theory. This is the definition of absolute logarithmic height, theta b n any non-zero algebraic number with minimal polynomial over Z is this polynomial, which is of degree L over Q. The absolute logarithmic height of theta is given this relation. And we need a lemma. This lemma comes from appendix of Diophantine paper, but the original result is coming from Laurent Mignon Nesterenko results, I think 1999 or 95, I don't remember. Diophantine gave this lemma. Using this lemma, sorry, I skipped the details. We have this linear form. Using linear forms logarithms, we get this bound, so this bound and this relation. So we complete the proof of theorem. These are main references. Thank you for your attention.
Thank you, Professor Soydan. Any questions? Anyone wants to ask? You can unmute and ask.
Hi, Gokhan. This is Pranavesh.
Oh, hi, Pranavesh.
Yes, how are you? Thanks for the nice talk. So
Thank you.
I was wondering, have you seen the latest result on sum of 3/5 powers being a perfect power? We have recently with Kutsianak.
Yes, Nikos Xenakis
and
Angelos
Kutsianak.
Kotsianak.
Yes,
Yes.
so we have generalized that Bennett and Peter Patel's work.
Yes.
Yeah. So
Very
I
nice.
was just like, bring it to your notice that possibly you haven't missed that paper. So yeah, I was just trying to bring it to your notice that possibly you might not have seen that. Yeah. Thanks. It's a nice result for squares, and you can certainly use a primitive divisor theorem for squares. But for higher powers, maybe it's difficult to use primitive divisor theorem. For example, cube or fifth power or seventh power.
Yes.
So have you thought about the seventh power case, like how to approach that problem for seventh power?
Seventh power?
Seventh power. So you have taken.
No, I have never tried.
Yes. Yeah, but for seventh power, one can still do some kind of modular argument. Yeah. So, but yeah, you may not be able to use primitive divisor theorem, but there might be a way using modular method.
Actually, I wonder if it's possible to apply to my equation x plus 1 to the key blah blah lx to the key is equal to y to n.
Mm-hmm.
You are expert about modular approach.
Mm-hmm.
Do you believe is it useful to apply it?
I think I'll have a look at it. It may be possible for your equation.
I mean this equation.
Yes, I know. I have seen this paper. Yeah, it's a nice paper. Yeah, I'll give it a try. Yeah.
Actually, we tried a computational approach for this equation. L is 2. Maybe you remember. It was published in Journal of Number Theory in 2018.
And I believe you used modular method, right?
Yes, Baker's theory. We used Baker theory with Berzesh and Istvan Pink. We did it.
Yeah. Nice.
Nice to meet you.
Yeah, nice to meet you as well. Thanks for the nice talk.
My pleasure. My pleasure. Where are you now?
I'm now in visiting Shanta, sir. Yeah, I'm in Delhi right now. Yeah,
nice.
I'm doing my postdoc in Waterloo, but I'm visiting India right now.
Very nice.
Okay. Bye-bye.
Bye.
Anyone else? If not, and so thanks, Professor Soydan again, and thanks to all the participants for joining us.
My pleasure.
Yeah, nice talk, Gokhan. So it's quite interesting to see the connection with Bernoulli numbers.
Thank you very much for giving me an opportunity. Thank you very much.
Thank you.